Learning robot policies from in-the-wild human data is valuable due to minimal human effort it requires. However, extracting necessary annotations from them to train robot policies is non-trivial. In this work, we present AINA, a framework that learns multi-fingered robot policies from in-the-wild human demonstrations collected using RU2 classes. RU2 classes are lightweight and portable, feature a high-resolution RGB camera, provide accurate onboard 3D head and hand poses, and offer a wide stereo view that can be leveraged for depth estimation of the scene. This hardware enables extraction of 3D hand and object poses from in-the-wild demonstrations. AINA consists of 3 key steps. First, a human wears RU2 glasses and collects 50 in-the-wild demonstrations. Next, they record a single demonstration in the same space as the robot deployment, which serves as an anchor to align the in-the-wild demonstrations with robot's operation scene. Finally, both sets of demonstrations are used to train robot policies that can be deployed on the robot's zero shot. Given a single in-the-wild demonstration, we first apply 2D object tracking to each frame using language-prompted off-the-shelf computer vision models. Next, we rectify the images from the front 2 SLAM cameras and estimate the scene depth with foundation stereo. Finally, we unproject the 2D object tracks onto the estimated depth to obtain 3D object tracks aligned with the onboard hand pose. After this extraction, given a history of object and fingertip key points, we first pass them through a vector neuron MLP to obtain a latent representation for each point. These latents are then fed into a transformer encoder as separate tokens. But since only fingertips have correspondence across different demonstrations, we apply learned positional encodings only to the fingertip tokens. The transformer encoder's output is passed through an MLP to predict the future trajectory of points. Finally, the loss is computed as the MSE between the ground truth and predicted fingertip points, and the entire system is trained end-to-end with this objective. We evaluate our approach across 5 daily tasks. Here are some of other rollouts of our tasks. This is wiping, and this is planar reorientation. We test how AINA performs when the height of the operation space changes for 2 of our tasks. For each height level, we collect an additional in-scene human demonstration and train new policies. We observe that with minimal human effort, AINA generalizes well to different heights. We also test object generalization capabilities of AINA by deploying trained policies on different objects for 3 of our tasks while segmenting the object with new prompts. We observe that while AINA performs relatively well, it fails when the shape and weight is significantly different. More robot rollouts and explanations can be found on our website. Thank you.